Welcome to the debate. When you think about what powers our modern digital landscape, it all feels entirely weightless.
Right. We picture like microscopic lines of code or, just massive amounts of electricity humming through these hyperscale data centers.
Exactly. We interact with generative AI systems on our smartphones, and we just assume this virtual space is boundless. But, this incredibly virtual ecosystem is actually physically anchored to a single, finite, non-renewable element.
And that element is helium.
Yes, helium. It is the ultimate invisible choke point. And to really understand the profound fragility of this entire system, we have to look closely at the events of early 2026.
The Qatar shock?
Right, the Qatar shock. Geopolitical military strikes directly hit Qatar's Ras Laffan industrial city. And for those who might not know, that is the undisputed global center of helium production.
Mm-hmm.
Following those strikes, Qatar Energy declared force majeure. They canceled all their export contracts. So in a single stroke, between 30 and 38% of the world's global helium supply was just instantly removed from the market.
Just vanished.
Overnight.
Completely.
And so, the central question we are exploring today is how to interpret the fallout from that catastrophic supply shock. Does this event reveal basically a hard, unresolvable geological speed limit on the expansion of artificial intelligence and advanced computing?
Or, and this is where I land, is this shock a painful but ultimately solvable forcing function? One that will drive the semiconductor industry toward, necessary supply chain resilience and closed-loop recycling.
Right. Because my position is that the laws of chemistry and geology place an absolute physical barrier on boundless tech growth. The foundation of our most advanced technology relies on an invisible gas that we are, frankly, entirely incapable of manufacturing.
And my perspective is quite the opposite. I argue that the bottleneck exposed by the Qatar crisis is primarily logistical. It's economic, meaning that market adaptation and, new recycling technologies will overcome these hurdles and ultimately fortify the industry.
To grasp the severity of this, we really need to start with the physical reality of the material itself. We are talking about a foundation of modern computing that you literally cannot synthesize.
Right, it's not a manufactured chemical.
Exactly. You can't just run a chemical reaction in a lab to produce more helium when you run out. It is strictly a finite byproduct. It's separated out in these microscopic trace amounts during the cooling and processing of liquefied natural gas.
Mm-hmm.
It has been trapped in ancient underground rock formations for hundreds of millions of years. So when Qatar's gas facilities went dark in 2026, that extraction simply stopped. And because its unique atomic properties cannot be substituted, the entire AI hardware ecosystem is inherently fragile. If the gas isn't flowing from the Earth, the silicone cannot be patterned.
Well, look, the severity of the shock is undeniable, and the geology is, of course, finite. But I would argue the vulnerability that actually fractured the market was entirely man-made.
Man-made? How so?
What broke wasn't the planet's capacity to yield helium. What broke was our hyper-lean, globally dispersed shipping logistics. We built an entire technology supply chain based on the assumption of cheap, perfectly timed deliveries. What we witnessed in 2026 wasn't the terminal exhaustion of the gas, it was the necessary structural end of cheap, single-use helium.
So you really see this as just a logistical failure?
Absolutely. Look at the historical context here. For decades, the global market relied on the U.S. Federal Helium Reserve, the cliffside storage facility down in Texas, to stabilize prices.
Right, the one from the space race.
Exactly. That government buffer was built up during the space race, but it was fully privatized and sold off in mid-2024. Once that safety net disappeared, the technology sector was completely exposed to raw market forces for the very first time.
I see.
The fabs were operating under an economic model where helium was cheap enough to just waste, and delivery was assumed to be continuous. So the Qatar crisis, which was definitely exacerbated by the loss of that U.S. buffer, is properly forcing the industry to abandon an unsustainable economic model. It's not signaling the end of technological expansion.
I hear you on the logistical vulnerabilities. I really do. But I don't buy that this is just an economic model we can tweak. You call it a logistical bottleneck. I call it a thermodynamic impossibility.
A thermodynamic impossibility? That's a strong phrase.
Well, let's look at the actual physics of transporting this material during the crisis. The production halt in Qatar was really only half the problem. Due to the regional conflict, the primary shipping route out of the Persian Gulf was closed.
Right, the maritime cargo ships had to detour.
A massive detour, roughly 3,500 nautical miles, around the Cape of Good Hope at the southern tip of Africa.
Right, which strained the entire maritime fleet.
But strain doesn't capture the physics of what was happening inside the hulls of those ships. To move helium efficiently at an industrial scale, you have to transport it as a liquid. That means chilling it down to minus 268.9 degrees Celsius.
Which is just a few degrees above absolute zero.
Exactly, it's incredibly cold. You pump it into highly specialized cryogenic vacuum containers. And here is the physical wall. Those containers operate on a strict, unyielding thermodynamic holding window. They can keep the ambient heat out for exactly 45 to 48 days.
Right.
A normal transit to Asian fabrication plants takes about 30 days. Routing around Africa pushed that journey to 44 days.
Pushing the containers right to the extreme edge of their specifications.
Pushing them to the point of literal failure. Think of it like trying to transport a block of ice across a desert on a ticking clock. Distance itself physically destroys the product.
Because of the heat leak.
Yes. When you hit 44 days, you are up against the absolute limit of that physical insulation. As tiny amounts of ambient heat inevitably breach the vacuum jacket, the liquid helium boils. And when it transitions from liquid to gas, it expands by a factor of about 700.
Which spikes the pressure.
Exponentially. To prevent the tanks from simply exploding on the ships, the relief valves have to open. During the 2026 crisis, up to 15% of the usable helium literally vented out into the Earth's atmosphere over the ocean before the ships ever reached their destinations.
Wait, let me stop you there, because I come at it from a different way. I acknowledge the venting was a catastrophic loss of material. And yes, the thermodynamic window is a strict physical reality of cryogenic transport. But framing this as an insurmountable barrier ignores the context of why that venting was so devastating to the factories.
How so? The gas was gone.
Yes, but the crisis inside the fabs wasn't just triggered by the 44-day transit. It was triggered because of ultra-lean factory practices. I mean, holding exactly 1 week of inventory on site at an Asian fab is a business choice. It is not a law of physics.
But when your supply chain involves a product that aggressively wants to boil away into the atmosphere, holding massive reserves on site is chemically perilous. I mean, it requires enormous, continuous energy expenditure just to keep it stable.
Expensive, yes. Perilous, perhaps, if mismanaged. But the reliance on just-in-time delivery for a highly volatile, cryogenically dependent gas was an economical calculation.
You think they just didn't want to pay for the storage?
For decades, it was cheaper for fab managers to risk a supply shock than to build robust, redundant cryogenic storage infrastructure on site. The venting over the ocean was an anomaly caused by a geopolitical routing crisis combined with a completely unforgiving inventory model. When you say distance destroys the product, you're right if we insist on shipping it halfway across the world to factories that refuse to hold more than 7 days of buffer.
So your solution is just better storage?
The solution isn't to declare the end of AI growth. It's to abandon ultra-lean logistics for critical raw materials.
Okay, but even if we completely solved the shipping crisis, I mean, even if we somehow engineered perfect thermal containers or teleported the liquid helium straight into the fab without losing a single drop, we still hit an absolute unyielding wall once the gas is inside the clean room.
Inside the fabrication process itself.
Yes. Let's look at the hard chemical reality of fabrication. Since helium is so volatile and difficult to transport, you'd think manufacturers would just swap it out for a more stable gas, right?
But they can't.
No, substitution isn't an option. The atomic properties are unique.
Exactly. You can't negotiate with the periodic table. During plasma etching, the tools generate intense, extreme heat as they carve the silicon. If you try to pump nitrogen into the chamber to cool the system, the nitrogen traps the heat and completely ruins the wafer.
Right. If you pivot to hydrogen, which, does cool efficiently, you are pumping a highly reactive gas into an electrically charged plasma chamber. It's essentially a bomb.
Yeah, not ideal for a multi-billion-dollar clean room.
Right. Helium is an inert, noble gas. It is the only element that can safely transfer that extreme heat away without reacting with the highly sensitive environment.
And those thermal properties become even more critical as the transistors get smaller.
Oh, the reliance deepens exponentially when we get down to EUV lithography. Printing these tiny, sub-5 nanometer chips for AI demands extreme ultraviolet light, and an EUV machine requires a continuous helium purge.
To keep the mirrors clean.
Yes, the system has to constantly flush its multi-layer optics with helium. Why? Because the vacuum inside the machine isn't perfect. Microscopic hydrocarbons outgas from the wafers and the internal components.
If even a single stray hydrocarbon molecule floats in front of that extreme ultraviolet light beam, the laser cracks the carbon off the hydrogen. You get a microscopic carbon smudge permanently bonded to a perfectly polished molybdenum silicon mirror.
Which is a disaster for the optics.
It ruins it. That single smudge absorbs the EUV light, blinding the optics, which ruins a $100 million machine and halts production entirely.
And, the hard drive sector faces a very similar chemical wall.
Yes, high-capacity data storage. The actual physical servers holding the cloud have to be hermetically sealed with helium just to reduce aerodynamic drag on the spinning platters. It's less dense than air. It's literally the only way manufacturers can pack dozens of platters closer together without the friction overheating the drives.
Right.
In every single one of these instances, plasma etching, EUV lithography, data storage, the laws of chemistry prevent a substitute. The industry has hit a hard production wall. You cannot innovate your way around the atomic properties of the elements.
Look, I hear the finality in your argument, but I'm sorry, but I just don't buy that. Let me tell you why. I agree completely that the laws of chemistry prevent substitution. Helium is chemically unique, but your argument assumes that because we cannot substitute the material, we are paralyzed by its scarcity.
We are highly constrained by it, yes.
I argue that this hard chemical wall is exactly why the industry's method of use is rapidly transforming. The chemical wall isn't a dead end, it's the catalyst for the next phase of advanced manufacturing.
How does acknowledging we can't replace the gas solve the fact that we fundamentally do not have enough of it?
Because it profoundly changes the economic calculus of how we handle what we do extract. Remember the single-use model I mentioned earlier?
Yes.
For years, you piped helium into the EUV machine, it swept away the stray hydrocarbons, and then it was exhausted into the factory exhaust system. Just wasted. But now that the gas is a premium, highly volatile commodity, we are seeing a massive directed push for helium recycling systems.
Recycling systems inside the fabs.
Exactly. To bypass future geopolitical shocks, semiconductor companies are actively spending hundreds of millions to install cryogenic distillation and membrane separation systems directly into their facilities.
Wait, are you talking about retrofitting existing fabs with entirely new chemical processing plants?
Essentially, yes. Think of these systems as massive industrial rebreathers attached directly to the fabrication tools. Instead of venting the gas after it purges an EUV mirror, the system captures the exhausted helium hydrocarbon mixture.
Okay.
It runs that mixture through advanced polymeric membranes. Because the kinetic diameter of a helium atom is incredibly small, much smaller than the bulky hydrocarbon chains, it just swept away. The helium passes through the microscopic pores of the membrane while the impurities are blocked.
So it filters it.
Yes. And then cryologic distillation cools a recovered gas just enough to freeze out any remaining trace contaminants. The system feeds the exact same newly purified helium directly back into the EUV tool.
Look, I see why you think that industrial circularity is the silver bullet, but I'm not convinced by that line of reasoning because let me give you a different perspective on how this actually plays out on the ground. Implementing industrial rebreathers and membrane separation sounds elegant in theory, but circularity cannot fix the immediate devastating downstream effects of a supply shock.
But it mitigates future shocks.
Eventually, maybe, but these recycling systems are highly complex. They take years to integrate into operational clean rooms, and they are never 100% efficient. In the meantime, when a shock like Qatar hits, factory managers are forced to ration immediately.
Rationing is just a temporary pain point during a transition phase, though. The technology works.
A temporary pain point. That temporary pain you're dismissing ripples through the entire global economy. Because fab managers must stretch their remaining helium supplies to keep the lights on, they have to run their plasma etching tools and EUV machines below optimal purge settings from week one of a shortage.
Right.
That rationing instantly increases defect rates on the silicon wafers. Suddenly you have a much lower yield. It becomes vastly more expensive to produce a single functional AI chip.
But the tech market absorbs those short-term costs. I mean, the demand for AI hardware is inelastic right now. People will pay it.
The market hides those costs until it's too late. Advanced microchips have a 12-week manufacturing cycle from raw silicon to packaged chip. So when the helium stops flowing in week one, consumers and enterprise buyers don't feel the supply drop immediately.
Right, there's a lag.
Exactly. It creates a delayed economic shockwave. 3 months later, the server clusters required for large language model development, the high-end electronics you try to buy, they are suddenly back-ordered and incredibly expensive. The entire digital economy hits a wall because 3 months prior, we couldn't properly purge a vacuum chamber.
And that precise economic pain, the delayed shockwave, the back orders, the skyrocketing spot prices for AI chips is exactly the forcing function I'm talking about.
How is economic damage a forcing function?
Because that financial damage is what justifies the massive capital expenditure for internal circularity. A decade ago, a CFO at a major foundry would never approve the budget for an on-site cryogenic distillation plant. It didn't make sense. Now, operating a high-end fabrication plant absolutely mandates this closed-loop ecosystem. Every single liter of helium a fab saves is a direct, measurable hedge against a volatile global supply chain and maritime choke points. Raw market forces are correctly incentivizing the fabs to adapt. We don't need to mine infinite amounts of new helium if we stop wasting the helium we already have.
But your argument fundamentally underestimates the scale of the expansion we are looking at. Yes, recycling helps extend the runway. I'll grant you that. But let's look at the actual projections. By 2030, the technology sector's demand for helium is projected to jump to 30% of the entire global supply.
That is a massive jump.
30%. Every single liter of helium required to initially charge the cooling loops of a new generative AI server cluster, or to fill a new generation of high-capacity hard drives, must physically be extracted from the Earth. You can't recycle gas you don't possess yet.
True, you need a starting volume.
Right. Recycling cannot outpace that level of exponential volume growth. Even if your polymeric membranes capture and clean 95% of the gas used in an EUV purge, the sheer volume of new factories coming online to support the AI boom demands a continuous, massive injection of virgin helium.
It is a steep adoption curve. I will readily grant you that. The volume requirements for new fabs are staggering. But the entire history of the semiconductor industry is defined by overcoming seemingly insurmountable physical and chemical barriers through massive directed engineering and capital investment.
But we aren't talking about engineering a smaller transistor. We are talking about basic elemental supply.
Yes, but look at the track record. People said we couldn't print features smaller than the wavelength of visible light, and we engineered extreme ultraviolet lasers to carve features smaller than a virus. If we can do that, we can certainly engineer membrane separation systems that approach near total gas recovery. We can build robust on-site storage. The 2026 Qatar shock was painful, but it was the wake-up call the industry desperately needed. It is actively transitioning the semiconductor supply chain from a fragile single-use dependency to a highly resilient, closed-loop ecosystem.
Well, as we draw this discussion to a close, my position remains that regardless of how advanced our recycling membranes become, the foundation of the digital world rests on a chemically irreplaceable, unmanufacturable element. It is bound by strict thermodynamic transit limits. Whether the liquid takes 44 days to slowly boil on a cargo ship, or the gas is constantly scrubbed through a proprietary membrane inside a clean room, we are fundamentally inexorably reliant on finite geology.
And my summary is that the Qatar crisis proved that while helium itself is finite, our engineering ingenuity and market adaptation are not. The actual bottleneck wasn't the Earth's crust. It was our own supply chain complacency. By shifting to industrial rebreathers and internal circularity, The tech sector is proving that market forces can decouple AI expansion from raw extraction.
It really forces a profound shift in how we perceive the weightless cloud, doesn't it?
Absolutely.
We tend to think of computing as pure mathematics, software, and energy, but appreciating the true complexity of advanced hardware requires looking simultaneously at cutting-edge multi-layer optics and ancient geological extraction. They are intimately physically connected.
Exactly. We invite our listeners to think deeply about the vulnerabilities hidden inside their own devices. The next time you use a cloud-based AI tool to generate an image or answer a question, consider the invisible noble gas that kept the plasma chambers from melting down to make that exact interaction possible. There is so much more to explore in how material science and geology govern our digital lives.
Indeed, we expect computing and artificial intelligence to expand boundlessly, forever pushing into the virtual unknown. But ultimately, that boundless digital future is tethered to a hard, unyielding geological speed limit.